today's workshop is going to be about network analysis. So what I will do is that I will briefly discuss some basic ideas, concepts in networks. And then I will talk about three main problems in the area. They are, how to measure centrality of nodes, how to find communities of nodes, and how to predict links. Right. So each of them is a broad research program. So I will only be able to scratch the surface here. But if you have any deep questions or specific research related questions, you're welcome to talk to me later. But now to make sure this works, so have you all played around with Notebook before? Let's just briefly introduce this notebook thing. So Python is a language, right? So you can write Python in any software, in any text editor, and here the notebook is one of them. So you can write your codes in the Python notebook, and then later you can execute it from inside the notebook, right? The nice thing about notebooks that it supports all kind of rich display format. Like here I can display text in different fonts, right? I can embed it code with my documents, like documentations, and so in order to execute this block of codes, what you can do is either press this play button here, or do Control plus Enter. Okay. Yeah. So then it's executed. Right. So Control plus Enter. Oh. Yeah. Okay. Now I guess I will skip this one because I'm not. All right. Okay. So no errors, right? I think we should all be fine because we're working on the same thing. And then here I'm gonna load an image here, which is a network. To do that, okay. So everybody is following. Okay, cool. Right. Okay. So this is a network, right? So what do you see? Is you see a bunch of connected dots with different colors and different shapes. But this is about what we are going to deal with in network science. It's just a bunch of connected dots, and people call them differently, in different fields. Like sometimes people call them like nodes, edges. Sometimes people call them links and vertices. Some people call them actors, ties. So in my eyes, they are the same thing, just different names, and I will use those terms interchangeably during this workshop. So when I say nodes, vertices, I mean those dots here. When I say links, edges, I mean the lines here, or their interactions, their connections. Okay, so this is a network, and this is actually a real network. I will tell you. There's an interesting story behind it. I will tell you later. But now let's keep going. So a network, could represent any system that has interacting parts, right? For example, social networks are typical examples of networks. We can also model like city road maps as a network, where you have cities here and you have roads linking them, or you can do protein networks. You can also model like the whole power grids as a network, right? In which you also have regions, and you have like power cables or power lines connecting them. So its network is a powerful representation of all kinds of systems with interacting parts. And you may wonder, right? Okay, okay, this is a picture of network then, but then how are they stored on computers? How can I really store network instead of just drawing them? There are two like popular formats to store it. Like the first one is ArgList. It's called ArgList, right? So it's just two columns of numbers, and each row corresponds to a link, right? And each row tells you the link goes from the first node to the second node. So like, there's a link between 1 and 2, a link between node 1 and 3, and so on and so forth. And this format of storing network is called arduous. It's the most memory efficient way to store it, right? Because you only store all the edges. So it's widely used, and we will use this later. Another way, which is also important and is easy for computation, is the representation is called adjacency matrix. Right? What it means, it's a square matrix. The number of rows and the number of columns is equal to the number of nodes. So in that way, you encode your network as a matrix. If there's a link between entry I and entry j, then this entry is 1. Right? This makes sense. For example, here, move this a little bit. Here you have the first row, second column. You have a 1 here. It means that there's a link between node 1 and node 2. Right? So the row means node numbers, and the column also corresponds to row numbers. And if there's a 1, it means you have a link between this node and this node. Right? It makes sense. So why this form is it's important for networks, because it allows us to do computations easily, and we will do that later. So now these are two basic forms to store networks, and you may wondering, so what if I have other attributes of nodes, right? Say their gender, their age, and you may have other attributes about links, right? Like the strength of link, the direction of the link. You can encode those information in. So there are other more powerful format to do it. Say graph ML is one of them. I'm gonna let me see if I can show you this. Go here. CI workshop. So a GML looks like this, So here you will have nodes, and they have IDs, so you can write, attributes inside for each node. And there are other formats such as JSON, but here just a brief introduction, because most of the time you don't need to make a network by hand by yourself, right? Most of the time you download a network from somewhere, or you generate a network from your program from other dataset. So it's very rare if you need to draw a network by hand. But if you do need to draw a network by hand, you can do it. You can write a text file as this, right? Say you have 3 nodes, you have 3 links, then you can write a text file, as an edge list, or you can write it as a adjacency matrix like this. So and also there's probably an easier way to do that, to make a network by hand, which is to use Delphi. And so that's why I have you install it. So we open Delphi. I hope, okay. So you'll have Delphi installed, right? So I think this one should be easier. So if you open it, you will see this. Okay, welcome to Delphi. I'm going to close this. So if you go to date laboratory, it's like a Excel spreadsheet. Okay, first I need to create a new project, and then I go to date laboratory. I can, then I can add nodes. So I give it a name, right? Say 1. I can add another node, give it a name 2. I can add another node, give a name 3. I can add an edge from 1 to 2. I can add another edge if you click that from 1 to 3, and so on. So this way you can build a network by hand very easily, right? So instead of writing out this adjacency list or something, you can do this in a more intuitive way, like dealing with a spreadsheet. And then if you go back, if you click overview, you can see, come on, okay. You can see the network you just made. 3 nodes, 2 links. That's it. So if you want to draw a network by hand, you can do it in Delphi in a very intuitive way. You can just add nodes and add edges, and you can see your nodes here. You can see your edges here, and you can see how your network looks like here. So, okay, and so since we have opened Delphi, I'm gonna use Delphi for a little bit. So, what is Delphi? So, Delphi is a very powerful tool in visualized networks, right? So for example, this picture here is drawn by Delphi. So it's not bad. And also, Delphi can draw very, very complicated pictures. For example, if you go to Knowledge Lab, so you don't need to go there, I will just show you here. So, for example, this picture is drawn by Delphi. It's the whole internet, right? So, it's kind of a piece of art. It's very beautiful, although I don't know what I'm seeing here, but it's drawn by Delphi. So Delphi is very powerful. That's the whole point I want to make. And Delphi can also do some like quick analysis. Right? So so with that, I will go into the second part, which is some exploratory analysis. Say if you got a network, right, you download it from somewhere or you generate it from your data, you get the network, and then you just want to do some quick analysis. You want to make some, pretty pictures about it. Then Delphi comes to hand. And so let's open. Okay, here's you. Okay, I'm gonna open this file called Karate Club, karate.gml, but I guess you don't have that file yet. So I guess if you go to the GitHub web page for this workshop, which is on this address, sorry for too many addresses, but this is going to be the last one. So it's on GitHub, github.com knowledgelab/ci-workshop-networks. So all the codes and data used in this workshop will be posted here, and you can, including all the changes that were made during the workshop. So later you can also go there to get the most recent version of it. But now if you go to the web page, there's something called download everything as a zip, basically. You can do that, or you can, just trying to download one file. But that will not work because GitHub's link is weird. So I think the only thing to do is to download the whole zip. If you click it, if you click download the whole zip, then you can download it to the place you like. After that, okay, let me do that. So let me download it to desktop. I go to desktop here, right? And then you need to unzip it. You get all the codes, all the data used here. Okay, so I hope you all get it. All right. So then I'm gonna go to Delphi and go to the folder and open this file, karate.gml. So what is this network? It's the social network in a karate club in a U.S. university. So it's a real thing. It's a real network. Okay, I'm gonna do this again. So it looks like this. And okay, it's a big mess. It doesn't say anything. So the first thing I would do is to give it a nicer layout, right? So a layout is a configuration of the position of the nodes. So there are many built-in layouts in Delphi, and normally I will use this one. If I run it, okay, then it's a little bit nicer. So it puts the nodes in better positions, so we can see the structure of a network better, right? Okay, so and there are many other things we can do, right? In Delphi, just some quick analysis. First, you can check how many components are there. So a component meaning a group of nodes in which every node can be reached from any other node, right? So it's to check if there are any isolated nodes or components. So if you click run, it will find like, okay, there's the run thing here. If I click run and choose undirected, because this is an undirected network, that will see, okay, there's only one component. So everybody can be reached from everybody else following the links. Right? So that's what it means here. One component, the network is connected. Okay, good. And there's other things we can do. So you can check the average degree. So what does degree mean? So the degree of a node means how many friends the node has. Oh, it's called karate.gml. Right. Right. Okay. Do you all have it running? Cool. Okay. Right. So okay. So what does degree mean here? Degree is how many friends the node has, or how many connection, how many link the node has. That's the degree. And the average degree, is the average across all the nodes. And if you click run, okay, it tells you average degree is about 2.3. So on average, a person in this club has 2.3 friends. That doesn't make sense, but on average, 2.3 friends. Okay, and then you can look at the diameter of the network. So what's the diameter? So in order to explain what diameter means, we first need to define the distance on this network, right? So the distance between two nodes on the network is going to be the path. It's going to be the number of links on the path, on the shortest path linking the two nodes, right? So that's just an intuitive, straightforward definition of distance, right? So distance is, for example, the distance between this node and this node is 1. You just need to go through one link. But the distance between this node and this node is 2. You need to go through 2 links. So that's what distance means. And the network diameter is going to be the longest distance between nodes, right? Or the largest distance between nodes. So what it tells you is like how large or how big the network is. So it says, okay, the diameter is 5. The longest path is only 5. It's not too long. And and probably you have heard this theory about 6 degrees of separation, right? So it means that everybody can be reached from everybody else through 6 other persons almost. So that's exactly what it means here. The diameter is 5, so which means the distance between any pair is at most 5. This is like a small society with 6 degrees of separation. And it also tells you the average path length. So diameter is the largest path or longest path. On average, the path length is only 2.4. Okay, that's okay. And you can also look at graph density, which tells you how dense the graph is, with 0 being the empty graph or empty network, and 1 being a full network. So here's 0.14 is relatively sparse. The network is sparse. And what else we can do? Okay, and the modularity here. So we will talk about this later. So what this function does is that it will find a partition of the network. Like, okay, so okay, if you run this, it will find a partition of the network. And what we need to do is to plot the partition. So okay, so it finds the partition, but it doesn't show up because we haven't told it how to show the partition yet. So if you click the partition tab here on the left corner, you can color the codes according to the community the partition it's in, right? So if you click nodes, click this, you can choose here modularity class. Then it will code the node according to the communities it's in, right? So if you click apply, oh, you see there are two communities, red nodes and blue nodes, right? Okay, and this is very handy. Oh yeah, so okay, so now I remember the story. So okay, so I said there's an interesting story behind this karate club network. The story is the following, right? So not long after the survey about the network has been done, this karate club actually split into two clubs because of a fight between the coach and the leader. So it turns out that the community detection or the modularity algorithm here, find the exact split that will happen later. So in some sense, if we know the structure, we can say, oh, we know it will split because it's two different groups of people, so they're different, so they will split. That's kind of neat, and that's kind of what network analysis is trying to say. It's trying to find like significant or meaningful structure of the network, so you can make prediction, understand the structure, understand the composition of the society or your network or your system. Okay, so this is some quick analysis, right? So using iGraph, using Delphi, you can do some quick analysis to see how your network look like. And we can also do one more thing. So here, nodes are colored by their community membership. We can also change its size. We can, if you go to the ranking tab, you go to nodes, and you can choose how to resize, rescale the nodes to encode other attributes. So here I'm gonna use the degree, right? So I need to click this thing here, which tells it I want to rescale the size, and then if I click apply, then the nodes will be rescaled according to the degree, according to how many friends it has. So we see a couple of big guys here. This is probably the coach, this is probably the leader. So they have lots of friends, they have lots of friend connections here, and you can see it clear from the picture, right? And okay, and the last step, which is my favorite, is in the preview window. And if you go to preview, then okay, nothing show up. You need to click refresh. Okay, then it generates the final picture you can use for your paper in Nature or Science. So that's how you get into Nature and Science, right? A beautiful picture. Okay. Yeah, that's probably that's pretty much what Delphi can do for you. So quick analysis, beautiful pictures. That will be it. So now let's go back to our real analysis. Okay, so yeah, okay, I just went through those things. It's network connected, the degree of nodes, the diameter, centrality, I will talk about that later. Community structure, we just see that in the karate club example, and the visualization using Delphi. Yeah, I forgot to mention this. And so Delphi is good for making static pictures, like what I show there, what you see here. But if you want to make an interactive, graph visualization, and you want to post it on your website, on your blog, so D3JS is the way to go, right? So here is an example. If I click it, this is a visualization made by D3JS, and you can actually, drag nodes around. So very powerful. It's fun, right? It's fun. But I don't have time to talk about that. That's a whole another story. That could be a whole another workshop on how to use D3JS because it's not only about visualizing networks. D3JS is a powerful library in JavaScript for visualization. It visualizes all kinds of stuff. For example, if you have read those articles about about informatics or data visualization in New York Times, they are all made by D3JS. Like those interactive maps, interactive bubbles and stuff. That's D3JS, so it's very powerful. But okay, just wanna point you to that if you need later. So now let's go to node centrality, and what does it mean? So one interesting or one important problem in network science is how to measure the importance of nodes, right? So in the email I told you that maybe not in the email you received, but in the original email I sent to Rob, I told him I will talk about the algorithm that has made billions of dollars. So you probably know what it is. If you don't, you can make a guess. It will be introduced here. So let's start by loading in the graph. So okay, let me before that, here's a little side note here. So to do network analysis in Python, there are two mainstream or popular packages. One is iGraph, which causes you a lot of trouble. The other is called NetworkX. The two are, there's no absolute winner, so they all have pros and cons. The iGraph, why I chose iGraph, because it's written in C, in the language C, so it's very fast. But also, but on the other side, because it's written in C, so it causes all kinds of trouble to installing it. It requires a lot of, dependencies, compatibility. So that's a headache. So it's a steep learning curve, but once you get through it, it's great. It's way faster, more than 10 times faster than NetworkX. Okay, but on the other side, NetworkX is good because it's written in native Python. So it comes with Anaconda. If you have Anaconda, you have NetworkX, you can do all kinds of things in it without any headache of installing it. So that's nice. It also has an active community. I am in that community, and I got hundreds of emails every day in this community asking questions. So yeah, so that's you can choose your whichever works better for you. But for me, I like iGraph because it's fast, and also because I'm also a R user. And iGraph, it's written in C, so it has an interface to Python. It also has an interface to R. So if I want to use R, I can just I can use basically the same code in iGraph in Python. I just need to change it, modify it to R syntactics. So this is sort of once you get around that steep learning curve, then it's easy, because if you know how to do network analysis in Python, you can use the same thing in R if you use iGraph. But if you use NetworkX, everything is different. All right. Okay. Okay. So hope you will feel better about iGraph after all the trouble it causes. All right. Okay. Now let's do some real analysis here. So first step is to loading a network, right? So you download the network. Again, you download the network, you generate a network. How do you load it in? So iGraph has many, like, how do I call it? Like loaders of networks of different formats. Like here, graph read PAYAC. It reads in a network in a specific format called PAYAC, which actually why it's called PAYAC, because there's another software called PAYAC, but that's another story. But anyway, so there's a specific format of network called PAYAC, and you can load it into iGraph easily. It's just one line of command. And here, if I do this, I didn't run this. Can you run this command? No, same error. David is not here, so that's bad. So it's yeah. All right. What I'm gonna do is I'm gonna restart my notebook. Oh no. Okay, so I'm gonna run it on my own. But for now, okay. So it turns out maybe it's because too many people are using it at the same time. We somehow crash the server or something. I don't know. So another bill is going to look for David, who is the server manager. So we will do this later. But now let me run this on my own machine. So this is a notebook on my own machine. It's the same notebook, but I just have everything installed, so it should work. If I do that, all right, okay, it worked. So if you have everything installed, you can run this. But if you don't, we will fix the server later, so we can run this later. But now if you run this command, right, you load in the network, and here this G simplify. Here G, you load in the network and pass it to the variable G, and you call simplify function here, which simplifies network. Here simplify means remove all the self edges and multi edges. So because sometimes the data you downloaded from somewhere may be noisy, so there's a link from a node to self, which doesn't make sense here. It also could be like multiple edges between nodes, and that doesn't make sense here either. So this function simplify remove all those sort of noisy link here. But sometimes multiple links and self edges do make sense, but they will not work here. So I remove them and I draw the graph. This is just a little function I made by myself in case iGraph doesn't work, but it's worse than that, I guess. The whole server doesn't work, so that's bad. So it draws this network. So what is this network? So it's those big families in Florence in the Renaissance period. So you can see, you may heard of some of those families like Medici, which is it? Okay, the Medici is very powerful in that period, but actually it started with less money and less power. So you can see from here. So here I'm gonna load in. So this part is not iGraph. So this command is from pandas. So if you ever played with data analysis with Python before, pandas is a powerful. Panda is an implementation of the data frame in R. Okay, so this sort of like goes in circles. So anyway, Panda tends to give you a data frame of your data. So like what Panda does here is that you read in this CSV file of information about those families and turn them into a table or data frame and show it here. So what you see those families, and you can see their wealth and their seats in the legislature and their marriages to other families. Okay, so the network here you see is about those families, and what are those links? The links are marriage ties. Like there's a link if there's a marriage between the two families, and you can see here, but the family Medici is actually not the richest, not the most powerful in legislature, but it is the one with the most marriage ties. So it's very active, or it strategically. So okay, so there's many research on it, but one hypothesis is that the Medici family gained its power in the end of the period by strategically improve its position on this social network to other families by making smart marriages, by making smart businesses with people, so they gradually improve their position and finally become like the godfather of Renaissance, right? So, of Florence, sorry. Yeah, so that's so then if we have an importance measure, it should be able to capture this, right? It should be able to capture to tell us that Medici is important in this network, because that's how it gains power in the hypothesis, in theory. So let's run through a bunch of centrality measures. I'm gonna explain them one by one and also apply them to this network to show you how it tells you about the Medici family. Okay, so the first centrality is just degree of centrality. So it just measures how many friends a node has. So this is the most simplest one. So it's a one line command in iGraph. You have that graph G, and you just call G.degree here, and it will calculate the degree of all the nodes. And again, I pass it to this Panda state frame, so it generate a table here. And also, yeah, I sort this table according to the degree. Okay, so you see, okay, Medici has the largest degree, so it knows a lot of people. So that's the first way of measure its importance. It knows people, okay? And the second one is called closeness centrality. It measures how easily a node can be reached from other nodes, right? So this is actually the inverse of distance, right? So the distance tells you how far you are from other nodes. So the inverse of distance tells you how close you are to the other nodes, right? So what they calculate here is that you add up the distance between me and any other nodes, and take the inverse of it. So that sort of tells how close other nodes are to me, right? So if I do that, another one-line command is all those measures are built in iGraph. So you just need to call the command to calculate it, and this is called closeness. And if you run it, it will calculate the canal. Yeah, maybe let me just show you what it returns. Okay, so if you call this command, right, it actually calculates the closeness for all the nodes in the network. Okay, I'm gonna delete this, and then I just pass it to this Panda data frame stuff, and then it will generate a table here. And again, you can see that Medici not only knows people, it's also close to all the other families. So it's really sort of in the center of this network. All right. Okay. And the next one is a completely different measures. It's called betweenness. Okay. What this means? So betweenness is the number of shortest paths that pass through me. So the betweenness of me is the number of shortest paths that pass through me. So what it captures is that how it sort of captures how much information will pass through me, or how much resources will pass through me. If you imagine that information pass through shortest paths, right? So, and also, if I have high betweenness, I'm sort of bridges between different people. So I not only gain information, I also sort of serve as intermediate between people. That's another measure of power, right? So if I do this, okay, I will get again Medici family has a very high betweenness. So it's between many. It's on the paths between many families. So if those family wants to talk, they need to go through Medici family. So another measure. Finally, we're going to arrive at one we mentioned earlier. So now, before that, this is the eigencentrality measure. Its idea is that how important I am depends on how important my friends are. Right? So this gives you this formula. So suppose xi is my importance, then my importance is the sum of all the xj's who are my friends. Right? So remember, aij is the adjacency matrix. Aij equals to 1 if I and j are connected. Aij equals to 0 if not. So here, effectively, you sum up all the nodes that are connected to I. Right? So this formula sum up all the nodes that are connected to I. So that's the idea of eigencentrality. And you can write this in matrix form. So it will turns out to be x t plus 1 equals to a x t. All right. And then if you do this, so you can continue this iterative process. You can multiply xt plus 1 by a. So if you do this over and over and over again, this vector x of centralities will converge to the eigenvector, to the leading eigenvector of the adjacency matrix. That's why it's called eigencentrality. Right? But those are technical details. You can Python, iGraph doesn't have a function to do this, but you can calculate this with any package that calculates eigenvectors. So you just calculate the eigenvectors of the adjacency matrix. It tells you how important the nodes are in terms of eigencentrality. Right? Okay. Finally, we'll arrive at this. So this is one, this is the measure that has made billions of dollars. Right? So probably you can guess from the name. It's called PageRank. It has to do with Google. It has to do with Larry Page, right? So actually, I don't know. I'm not sure if the names come from Page or something else, but it is what Google uses in the early days, right? Okay. So its idea is similar to the eigencentrality. The idea is the following, right? So how important I am or how important my web page is depends on the importance of the websites that link to me. Right? So if a lot of important websites link to me, then probably my website is important. And that's the first part. And also the second part here is that, one caveat with what I just said is that, Google links to other, not Google. So before Google, say Yahoo links to a lot of websites, right? So probably Yahoo links to my websites too, but my website is not that important because Yahoo also links to billions of other websites. So however, if you think this as a voting process, so it's like Yahoo vote each other websites by linking to the other websites. It's sort of like Yahoo gives out too many votes, so his vote or her vote, Yahoo's vote should be discounted. Right? So the idea is that the importance of my website depends on which websites links to me, and also depends on how many links they send out. Right? So Yahoo links to me. Yahoo is important, but Yahoo also send out like billions other links. So each link only get a fraction of Yahoo's importance. So that's the basic idea. And then the only change here, forget about alpha and beta. The only change here from eigencentrality is that you divide the importance of your friend by how many links he or she sends out. Right? So that's what K out means. So if it sends out billions of links, then its importance is diluted. Okay, so and then here, why is there a beta here? Because this is like a free boost of my importance. Here, xi is my importance. It depends on my friends. And here, beta is like a free food, a free lunch, or free boost of my importance, just a parameter here, right? You add beta. So, and then you can also write this out in a matrix form. And then if you do this over and over and over again, it will give you the importance will converge to the stationary probability of a random walk visiting each web page. So if you imagine there's a random surfer who just click links randomly on websites and follow them. So what this measures gives you is that the probability that the random surfer visit each page for a web page, right? So that's why it's also called, sometimes it's called like random walk centrality in some cases. Yeah, but anyway, iGraph can also do it in one command. It has a built-in function. It's called PageRank. So if you do it, okay, it gives you the PageRank centrality of all the nodes, right? Again, but this, if they have Google in that period, if they search in Google, then Merdich will be the first to pop up, right? So, okay, it's again. So, okay, so yeah, this is sort of, I mean, there are many modifications and variations of those centrality measures, but those are sort of the main ones that people use nowadays. And especially, PageRank has been very successful, right? Because before Google, what the search engine does is that they're just trying to find keywords that match the search keywords, right? So they're just trying to match content. But the problem with that is that you can game in the system, right? So if, for example, someone search for word, and for word Merdich, and then in your website, you can just put down a empty website with 100 Merdich on it with nothing else. Then the web engine with only match a search engine that only try to match keywords will find a web page with 100 Merdich is probably important because it's mentioned 100 times. So what Google does is that, okay, so what Google says is that, okay, now I'm going to try to find all the web pages that has the keywords you search for, and then I'm going to rank those pages according to the PageRank, right? So in this way, it seems to does a nice job because it takes advantage of the links between the connections or interactions between web pages. And of course, that's just the first algorithm. And now Google has a very complicated machine learning algorithm integrated or incorporated with this to predict the rankings, to make rankings. So, but this is the basic idea. And it also shows, the power of network analysis. So not only content matters, but also connections between content or items matters too. And sometimes it's even the connections between your system or your items matters much more than content in it. Okay, so that will be it. Bill, did you find that? Okay. Okay, let me. Yeah, it was working. We tried it, but now I don't know why. Okay, let me give it a try. Hopefully, it's fixed. All right. No. Okay. Okay, sorry for that. Technical difficulties. Right. So okay. So this is about how to measure centralities, and the next problem is how to find meaningful structures in networks. Like what I showed you before in the Karate Club example. By looking at the structure, you sort of can predict, the split. You sort of knows what structure it is. And what we use in the Delphi software is this algorithm called modularity, right? What it does here, what modularity does is that it finds the partition of the network that maximizes this quality function called modularity. That's why it got its name, modularity. So this function is called modularity here. It measures how good your partition is, of the network is, right? So if you, okay, so just a little bit details here. CI is the community number that node I is in. CJ is the community number that node J is in. And here this delta function is a delta function. It's equal to 1 if I and J are in the same community. It's equal to 0 if not. So what this function does is counting up how many edges are there in each community, and then add them up. Right? So we, without this negative term here, negative term here. So if there's no such term, if all you have is aij time this thing, the best partition would be the whole network, right? So because in that case, if the whole network is a community, then you have then this this quantity will achieve its maximum, because you have everybody basically count up all the edges. So that's just boring and trivial, right? So what this term does here is that this is a smart term, because so now instead of directly counting how many edges fall into each community, now you are counting how many edges fall into each community compared to the number of edges if the network is random. So all this term does is a quantity that tells you what will happen at random in a random network, right? So what this does is that you count the number of edges that's more than random in your network. So anyway, this term does the magic that it finds the meaningful structure in many real networks. Okay. So now we're gonna do a fun analysis with some interesting data, not ancient, Florentine data. This is recent Facebook data. So this is the Facebook in Caltech collected in September 2005. Okay, so now I'm gonna load this file, Caltech, the text is the social network, and I can show you what it looks like. So this file actually, this looks like, it's the edge list I showed you before. It has all edges, and it's just 2 numbers per row. Okay, so I can load in. So it is a function called read edge list. I can read this file, and also I simplified it too. Okay, then I got it. And the diagraph has a function called summary, which sort of gives you a quick summary of the graph. There are what it means here is that there are 762 nodes and 16,651 edges or links. So okay, quick summary. And since the network is too large, I'm not going to plot it here because you will see nothing instead of a horrible what will go on. And I also have other side information about the people in this network. Right? So in this case, I know where the people lives in. I know which dorm they live in. So I'm going to reading this information. What I'm going to do is that this opens this file. We can show you what this file looks like. So this tells you which dorm each person lives in, in order. But it's all coded. So to protect privacy, it's not the actual dorm names. It's just the code name. Don't worry. We don't have your data. You're safe. Okay. That's it. So what I'm doing is I open this file, right? And I going through this file line by line, and then I take each line. Each line is a dorm, right? And then I pass it to each vertices, each nodes in the network G. So here G.VS, will give you the vertices, okay? And the G.VSI will give me the ith vertex or nodes, right? So and then I give it a attribute called dorm, and then I assign the dorm to this attribute. So okay, so this is how iGraph works. You have a network G, and you can look at its nodes by G.VS or vertices by G.VS, and then you can look at the specific vertices by give it an index like node I, and then you can set its attributes any way you like. Okay, it's very convenient. So now now I have the network. now I know which dorm each person lives in. What I'm going to do is, okay, now I'm going to do the modularity community detection algorithm. This algorithm here, basically I'm trying to find a partition of the social network, of the Facebook network, that maximize this quantity. Okay, so I'm going to do that. Okay, it's done. Okay, let me just do everything again in case. Okay, and then what I plot here is the distribution of dorms in each community. So what it finds. So okay, so here, okay. So how do I find communities? One line command, g.community, using this method called leading eigenvector, and then I get the community, and then I can plot like the distribution of dorms in each community. And what you will see is that, okay, so in total, I find 7 communities or 7 groups of people, and I look at how are they distributed, how are those people distributed in the dorms, and you can see that okay, like this community, most of people in this community live in the yellow dorm. Most of the people in this community live in the gray dorm. Most people here live in the blue dorm, and so on and so forth. So it turns out, the people on our social circle, especially for college students, is very much driven by where we live in. Where we the people we know, we interact daily, are people from our live together or live close to us. And one strange thing here is the white space. It's everywhere. It's in all the communities. And what are those things? The white spaces are missing data. So those are the people who refuse to fill out which dorm they live in. And the shocking thing here is that by doing the community detection, we can infer which dorm they live in. Isn't that sounds sort of creepy? Because those people are trying to protect their privacy. They don't want to tell people where they live in, so they don't feel that on Facebook webpage. They think their privacy is safe, their information is safe, but not, because they interact with other people. So we can infer about their dorm in this case from their interaction with other people. So like here, if I interested in someone here, I know she or he probably lives in the yellow dorm. The people here probably lives in, the red dorm or this light yellow dorm. So yeah, so this is what community detection does. It finds meaningful structure in the network, and this structure usually tells you something about the network. It either tells you, like a function module of the network, or it tells you how people interact with each other. And then using the information, using the structure information, you can further infer people's interactions and attributes. So okay, so that's what it does. And the last thing in this section, okay, so this is one way to find communities. There are like many other ways. There are probably more than 10,000 papers on how to find meaningful communities and networks. And so that's just, I just showed you one method, and here I list 5 like different methods. This one called InfoMap. I mean, okay, but the nice thing is that, so I don't think I have time to go through them one by one. So yeah, they're just different methods, but luckily iGraph has implemented most of them. For example, InfoMap, it's in iGraph. Yeah, everything is in iGraph except for the last one, stochastic block model. So it's nice here. It's nice to have multiple methods, right? Because if you have a data set, you want to find, meaningful structures. Say you have a gene interaction network, you can apply different methods to them to find meaningful structures to help you find, for example, like gene modules that corresponding to some cell functions, and so on and so forth. So having multiple methods will reduce the bias or discrimination, because different method will find different kind of structure. They have different objectives in their searching, in their searching algorithms. So you can try all of them or some of them and see, what's the different structures you find, what's the consensus structure you find, and they're all in iGraph, so they're ready to be used. The last part I want to talk about is link prediction. So it's also a broad area, and there's a bunch of link prediction algorithms. There's a bunch of features you can use to predict if two people will be connected or if two things will be connected in the future. So, for example, you can look at how many common neighbors they have, like how many common friends they share. That's sort of like what Facebook uses to recommend, people you might be interested in, sort of things. So one feature it uses is how many common friends you two have. Right? And the second thing, another thing is called Jacob similarity. It normalizes the number of common neighbors by the number of neighbors you two have. So it tries to it works similarly with common neighbors, but sometimes better because it normalizes with the size of the neighborhood. And there's also this thing called academic DAR score, and you can use distance. You can use, so those things. I'm gonna skip this because now we way past through those features. What we're using right now is called this matrix factorization method, and it's mainly what Amazon used to recommend their items to you. And this is also, this algorithm also finds successful application in all the recommendation systems, right? Like Netflix, Amazon, eBay. So anywhere where they try to predict where you will buy, what you will buy next, what you will like, this sort of stuff. And this general frame of methods is also called collaborative filtering. The idea is to use people similar to you, is to compare people similar to you and use their preference to infer your preferences, right? So if you look at this picture, right? So there are two types of nodes here. The first type is user. The second type is items, books, music, like here video games or etc. And we know that which people bought which thing, which people like which item, right? So this is like we call it bipartite network because there are two types of nodes, and a link only runs between a user and an item. So using this network, right? So given the whole purchasing history or your preferences, can we predict your preferences or your attitude on an item that you haven't seen before? You can also write this matrix write this network in a matrix form, right? Basically, you have users, you have items. Which user likes which. This user likes this product or not, right? So the idea is to predict, okay, what this guy would like between these four things. So I can recommend this product to him if he likes it. Right? So if I can predict this very, very precisely, then the user will buy more stuff. Right? That's the basic business model of all those online sellers. So how to do that? It's called the method. The basic idea is called latent feature or latent space method. Basically, the idea is to assume that each node, each user, or each item has a position in a latent space. Right? For example, a movie could be, in the space of say 80% action, 20% romance. A person could be in a position of, yeah, so still in the movie case, a person could be in a position of, say, 10% suspension movie, like 90%, animations or something like that. So assume that, there's a latent feature, which is usually, more subtle than genres in the movie case, right? So that's why it's called latent, because it's not, it's subtle. It's not what we can see. It's in the data, and what they trying to do, what this algorithm tries to do, is to find this latent space. Is to infer it from the history of all the purchases or preferences, or so this is the basic idea, right? So okay, I just went through this. So suppose you have a matrix A that tells you which user likes which item, and which user haven't bought which item. So, and then assume each node, each user and each item has a position. So assume each user I has a position pi, which is a vector, which is its coordinates in this feature space. And suppose each item j has a position 2, and then the how user I likes item j is a function of the similarity between their positions in the latent feature space. Right? So it's a product, it's a dot product of the two vectors. Okay, so and then the whole problem becomes to infer, is to approximate A by this two matrix P and Q. So that's why it's called matrix factorization, right? Because you have this rating matrix A, you have some entries missing here. You don't know, this person hasn't viewed this item before, and then you try to infer the user's position and the item's position, and then when you multiply them together, it gives you it filling out those empty, this blank links, and the way it fills this blank entries is to assume that how user I rate item J based on their their positions. Okay, so that's the idea. And then how to do that? You can run that. The idea is to, of course, is to find a factorization of A, but how to do that really in computers? So it's trying to find PIs and QJs which minimize this cost function, right? So here it's or this squared error function. Okay, so here I found a piece of code online. I'm just gonna run through a simple example. For example, here you have those are the members of Knowledge Lab, and those are the movies they have or haven't watched, right? So here, 5 means like it very well, and 0 means we don't know, right? 0 means the person hasn't watched the movie yet. So okay, and then what we're gonna do is we're gonna infer the latent positions of each item and each node. So in other words, we're trying to find PIs and QJs that minimize this function. So it's down through this function, and then I will run it here. So this is a function that find the optimal P. I call it PH and QH. Okay, so here I just gonna do it. It will take some time. Okay, and then it finds the latent positions, and then when I multiply these two matrices together, it fills out the missing entries. Oh, I just did that. Okay, you see it fills up the zeros here. It replaces zeros by its prediction about the user's attitude of the movie. So, and also For the ratings, we already know. You see, it's not exactly gives that because it's approximation. Like here you have 5, here you only have 4.9, but it's very close. And here you have 0. You don't know anything about this entry, but here it tells you, okay, probably the user will, it's the opinion is moderate about this movie, but here you have a 4. It tells that, okay, this user probably likes this movie. So if you're running a recommender system to sell your stuff, you probably should recommend this item to the user. All right. Okay. And all right. So I guess that's as I said, I just briefly reviewed all kinds of algorithms in network analysis. So they're just they're very they just barely scratch the surface. But I hope the message, the take-home message is that I hope to convey is that what can be done and what cannot be done in network analysis, and also you have leads to those algorithms when you need them in your research in analysis.